In next 5 minutes, I am going to explain you all types of time complexities and importance of it. So let's get started directly. The very first we have is a constant time complexity, that is O of 1. That means algorithm doesn't depend upon the input size. It is most likely the formula or conditional statements, assignment operations or arithmetic operations, right? Remember, the code length has nothing to do with time complexity. The time that you take to understand the code has nothing to do with the time that machine takes to execute your code. Look at the bubble sort and merge sort. Bubble sort, code is only 3 to 4 lines. But time complexity is n squared. While on the other hand, we have merge sort. Code is lengthy, but time complexity is n log n. So code length and execution time have no relation at all. Second we have is log n time complexity. Now we know that we have already seen in logarithmic video. I will put that into the card. Log n means number of times we need to divide n by 2 till it becomes 1. That's what log n means, right? So most of the times what we will be doing is we will be using a divide and conquer technique to divide the input array by 2 till it reaches 1. That's why our time complexity is log n. Most of the times, okay? Then we have root n. Usually we have a loop that ends in this type of condition. This we already saw in factor computation. There is something called square root decomposition. We are going to see all these algorithms. See, why I am highlighting all these standard classes is because these are the highly used time complexity classes into competitive programming. Most of the time you will see your algorithm falling in one of these categories. That's why I'm trying to explain a general way of looking at it. O of n is definitely greater than root n and log n is the fastest one. What is O of n? Well, usually we are looping through every single input element. That's when we have this O of n type of time complexity. After that we have n log n time complexity. Mostly sorting algorithms take n log n time complexity, like merge sort, quick sort. They take this n log n time complexity. So you might be using somewhere sorting algorithm. There are various other algorithms as well which takes n log n time complexity, like segment trees. They take log n time complexity to answer a single query, right? And you might be processing n different queries. So your time complexity is going to be log n log n. After that we have n square time complexity. Now this is a polynomial time complexity with power 2. This mostly happens because of two nested loops, and we are visiting every single combination of pair I and j. Then we have 2 power n, where this indicates that we are iterating through all the subset of the input. Like let's say this is the input that we have 1, 2, and we are iterating through all the subset of this particular input. 2 to the power n means most likely our algorithm is iterating to all the subset of input elements. Most likely. This is all that we are seeing now. These just most likely scenarios. You can have n log n time complexity even without sorting, or there is no involvement of segment or binary index t and you can still have n log n time complexity. So we are looking at the various classes of time complexity and we are going through most likely scenarios. After that we have n factorial. Let's say this is our input 1, 2, 3. And if time complexity is n factorial, most likely you are iterating through all possible permutation of the input. Like these all are the possible permutations of the input, right? That's when we have n factorial time complexity. N power k, this means that algorithm has polynomial time complexity. Except for 2 power n and n factorial, all the other time complexities that we just saw are exactly polynomial time complexities. If k is small, that means our code is going to run faster. So we need to reduce the k and find the most efficient algorithm. So there are some algorithms for which there exists no polynomial algorithm. They are called as NP-hard problems. There exists no algorithm that can run in polynomial time for those few problems. We call them NP-hard. So we have gone through the most commonly used time complexity classes. Our objective was to look at these time complexity classes and understand the most common occurrence of this.